Quick review, okay? Just step back and then we'll move forward very quickly. That is, I want to just talk a little bit about inertia again, okay? Which is, when we were talking about linear motion previously, inertia, inertia is resistance to a change in motion. Right? I think that's a good. Inertia is resistance to a change in motion. So, if you have an object sitting here, the larger the object, the harder it is going to begin to move it. Right? The smaller it is, the smaller its inertia, the easier it is. And we measure inertia that way in mass. Okay, so if we have a large mass, it's harder to get it moving than a smaller mass. Inertia. Now, applying that in a rotational sense, we have what we call rotational inertia. Rotational inertia. And that is opposition to beginning to move something, excuse me, to move something in a rotational fashion. So if you have a big grind, potter's wheel, did someone say here they worked with pottery? I guess it was the other class, where you have those wheels that you get going, right, because you're going to do something with clay. Once they get moving, they have a large moment of inertia, they're going to keep moving usually. They keep moving for a long time. Rotational inertia is not measured just in mass, kilograms. It's also measured in the distribution of that mass about the axis of rotation. And its units are kilograms meters squared. And the same object can have different moments of inertia, which means it can be easier or more difficult to get them rotating. Who was it that was rotating this thing? Who rotated? You? Okay, so you found it easy to rotate. This is one object, has the same mass. If you use this axis here, it was very easy to rotate, right? Yes. And then when you rotated about an axis here, you found it a little more difficult to rotate, but you could do it if you were fairly coordinated. Were you coordinated? Huh? He almost hit me. Right, that's how coordinated it was. Okay. But when I asked you to move the axis over here, so you had to move it like this, it was very difficult to rotate around. Large moment of inertia, right? It had a much larger moment of inertia, even though the mass is exactly the same object. Okay, so you have to consider the axis of rotation when we're talking about rotational inertia. All right, I have a question. There are two pendulums back there on that wall, okay? The moment of inertia, for a pendulum, okay, can be calculated. I is equal to mr squared. Now, each of your groups, you have, 5 groups here, should go back there. I'd like you to determine what the moment of inertia is for both those pendulums, assuming that what they're hanging from is massless, that the mass is really concentrated at the bob there, okay? And I think the mass of that is 440 grams, 4.4 kilos. Yeah, let's just say the mass of this, each one of these, so you have to double them, is 2.4 kilograms. Okay, so that's 2.4 kilograms. So it's 4.8 kilograms is the mass of this. Don't worry about the mass of this here, this line. So here's a couple of rulers. Tell me, all right, what is the moment of inertia of both these pendulums? Okay, and you can calculate it here. R has to be in meters. And after you've determined the moment of inertia, your group should decide which one will rotate faster based on what you've determined the moment of inertia to be. Where's the axis of rotation? All right, up here? Okay. So go ahead. You have a couple of measurements you want to make here.
What are we calling the mass?
The mass is, what is it? 4.8 kilograms. So the shorter one and the longer one. What's the moment of inertia of the shorter one?
1.45.
Say it again.
1.45
And what are the units?
kilograms
Kilograms,
meter squared.
meters squared. And the longer one?
4.33.
Kilogram, meters squared. Okay, so basically we have the same pendulum. They have equal masses, actually, but the distribution of their masses are different about the axis of rotation. One is almost 4 times greater than the other one, just coincidentally. Okay, so which one has the largest moment of inertia? The long one. Okay, so in terms of resistance to rotational change, which one is more resistant to rotational change? The longest ones, which means its swing about its axis of rotation will be faster or slower. Okay, check it out. Could someone kind of move them both about the same angle and let's see what happens? Are you fairly coordinated? Did you do? Okay, let's keep an eye on this guy. Whoops. Let her rip. Which one is slower in its rotation? Perfect. And you see why? You guys are good. Very nice.
Can I ask you a question while we're at it?
Okay.
We're assuming here that the axis is all the way at the end
Yes.
of the mass, right? Okay, well, all the way at the end of the stick that's holding. We didn't actually consider the rod itself as
We didn't
part of
consider the mass of the rod, right?
Okay, well, here's my question for our demonstration later today. If you have a mass at both ends of a stick and your axis is in the middle somewhere, what do you do with those calculations? Add them or make one a negative and add
Yeah.
them?
Yeah, they're
How do you do
opposite
that?
each other.
You're opposite. You have a very odd-shaped object that has a moment. I'm not really sure exactly mathematically what you would do because all the objects that we deal with are very symmetrical and easy to handle mathematically. I'm sure there's a way of handling it. I don't know the answer to that, but you can look it up maybe.
What about a twirling baton? Usually
Yeah, you have
one
2
end-
weights.
Yeah, but one's usually bigger.
Is that right?
Yeah, I think one's smaller and one's bigger on the sides are different.
Batons?
Yeah.
Yeah,
They are.
okay.
And do you always hold
they
it
don't twirl.
exactly in the middle?
Well, I don't know how they.
Or do you hold it so that it's balanced more, so that you're closer to the heavier weight? I don't know. I haven't never.
Okay, so during our presentation.
Yeah, I hope you know the answer because I'll ask you that.
We're gonna be shooting some bullets and you can't catch it.
Okay. Now, are you referring to the baseball bat issue?
Yes.
Okay. I think you can, when you choke up on the bat, you can, as we neglected the mass below the pendulum here,
Right.
you can neglect it as being inconsequential to the overall concept.
Well, it wouldn't be, I mean, I think depending on how far you're choking up, because if you had this, I don't know, if you had it like this and put a weight up here as well,
Yeah.
then that.
But
would be-
you
that would be
see,
a kind of situation.
but you see, that's exactly what this one is over here, because the weight,
Well, no, except there'd be a weight up here, acting as a. some
oh,
kind of-
on the opposite
Right?
axis of
Can I
rotation?
Yeah, I mean, if I could remove this.
No, don't remove them because they're really hard to put back on.
That would be the situation.
Yeah.
Where we have something up here.
Yeah.
too.
And not only that, you probably have different weights and different lengths.
Right, and we'd have to guesstimate.
Yeah.
how much of
What you're
that
talking
is
about
on
is-
one side of our hands and how much is on the other, but.
What you're talking about is a 2 torques, which we're going to maybe cover a little bit today, if not today, later on.
All right, well, don't ask any hard
Okay.
questions. If we're,
Everyone knows now not to ask any questions on that, right?
The mean people will ask questions.
Okay, so anyway, the general idea in a very simplistic fashion with not anything extraordinary like that, or considering also the mass of the rod, because there's mass below the pendulum on that one there. But in very symmetrical terms, it's easy to calculate or determine, relatively speaking, moments of inertia. So as I mentioned yesterday, the stick moment of inertia varies by a factor of 4 depending on whether the axis is in the middle or on the end. Again, very simple, no extra weights or anything of that nature. Okay, now I have a question for you. I have two objects. All right. They're both relatively the same mass. Right. Not roughly, I don't, yeah, it's about the same. And they also have, look, right? So their axis of rotation about the center is very similar. And if they rotate this way, I'm not going to rotate them this way. Right? All kinds of axes of rotations here. But so if I have a hoop, right? Hoop. And this actually is a solid disk or a cylinder. Okay, so here's the moment of inertia for the solid disk or the cylinder. Yeah, open the windows if you like. Okay, so here are the two moments of inertia. And without giving you any numbers, all right, I'd like you to tell me which one will reach the bottom, that little incline there first, if I start them together, and then have someone demonstrate. So first we want to decide in your group which one is going to reach the bottom first, and then we'll try it out.
Is the mass uniformly distributed in the black one?
Yes.
Because we have a physics teacher.
Yeah, I know, but I'm not doing
who
anything.
has one with,
Yeah,
with an
it's
uneven
weighted.
distribution in the center.
Okay. Very cool. Okay. So talk within your group a little bit. You know, and why? You know, I want to know. Don't just. Okay, but in your group. Okay. So what's your thoughts first of all? Which object has the larger moment of inertia? Which one?
The ring.
Okay, everyone in agreement? Okay, so this has the larger, this actually has half the moment, right? So which one will reach the bottom first? Okay, let's see.
And go.
Did you see it?
Nice being right.
We didn't say it.
Do it one more time. Wait a minute, let me get a picture of this. Hold it, wait a second. I got to document this for camera.
Sorry.
Oh, you're out of the picture, huh? Oh, this one,
I
okay.
want to have a line of these.
All right, go for it. Oh, my camera's so slow.
Video it. Video it.
I will, all right. Hold on a second, hold on. Video, camera.
Now, is this because of the, like, with the thing with the cup?
What?
Weight,
Oh, yeah.
where the weight is farther away?
Where'd my video
from
came?
the axis of rotation
If you-
in the ring?
The reason I asked her whether the mass was evenly distributed in the disk is because
Yeah,
a
all right.
significant portion of the mass is close
Now I'm
to
taking the
center.
picture of myself.
That reduces the moment of inertia.
Smile. Okay, so tell us what you're going to do and why.
We are testing for which will roll to the bottom faster based on moment of inertia on the two differently sized or shaped discs. Actually, they're not different sized or shaped.
Actually,
Differently
they're the
distributed
same. They're the same
Differently
weight.
distributed weight.
Okay. Which one won?
The solid disc,
Why?
because it has half the moment inertia of the ring. Based on your.
Well, the reason it has half the moment of inertia.
Forget it. I got it. Very good. Okay. So you were able to think through, which was really good, which one would have hit the bottom first because of its moment of inertia, when in many cases, someone might think, well, the hoop, it looks lighter, therefore it'll go faster. Some people might think that, but that's not the case at all, right? In fact, it was the solid disk that went and achieved the bottom first. Okay. Let me pose another, whoops, so there you go. You have all that, the disk. Okay. I have, as soon as I go and get it, 2 cans of juice. One is defrosting and one is still in the freezer. And my question for you now, amongst your group, is which one will reach the bottom first, or which one will come down faster? The frozen one or the one that's liquid? I'm going to go and get it right now. So you want to think about it. Okay. You have any ideas? Frozen one, kind of liquid. Both the same. All right. Pink lemonade.
How was the frozen one frozen on its side or laying down? Or?
Actually, it was laying down in there, but it's actually not that frozen anymore. But it's I consider it to be solid. It's as solid as I can get it. That stuff doesn't really freeze really, really, really hard. So I hope this works. What are your thoughts? They obviously have the same mass, and the distribution of the mass is relatively the same in both of them. Right? They're pretty full. Any thoughts? Would they go down the same?
The frozen one, in theory, should get there first.
You have something about the water, what?
We're talking about how water expands.
Okay. I don't think that has a role in this, but okay, good thought. Anything else? You think it's the same? Could it be the same? In terms of moment of inertia, you're looking at, again, the mass and the same distribution of the mass. So it's almost like the moment of inertia looks like it's the same.
Except that if the fluid one, is the weight of it's going to be towards the outside and the it's going to stay to the bottom, away from, it's going to be unevenly distributed.
Okay, that's a good point, and I think that's a valid point. There might be some uneven distribution, unless I could get an object that was really, really perfectly full of water. Obviously there's a little bit of air in there. Anything else?
Will the liquid move? Like, you think when it's spinning, it might, because if you have a glass of water or whatever and you have ice cubes in it, if you spin the glass, the ice cubes pretty much stay the same.
Ah.
So maybe it doesn't slosh around like you would think.
Okay.
It stays there.
Yeah, so there's some concern about the liquid nature of the matter. So which one is going to hit the ground first? Get to the end or go down faster.
Frozen.
Frozen, how many say frozen? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And how many say, obviously, liquid? Come on.
Faster?
The liquid people are not as sure. They're not, put their hand up. All right, so
About the same.
how many say about the same? Hey, okay. Can we have a demonstration? Oh, you have a question? Come on. You get to keep the lemonade. Yeah, you could. Yeah, I don't know if you could do it with that, or maybe you could just do it with your two hands. So tell which one is which. I'm sorry if I'm standing in people's. Which one is which?
This one is the frozen one.
The one closest to us is the frozen one?
Yeah, this one.
Okay, let her go. Which one?
Same.
It's probably not liquid enough or not long enough. Let's get someone up here really watching closely. Can you see it really good? Okay. They all both the same? So now it's critical. We have to get them both going at the same time. And they're not touching the edge of the bird at all on the back side?
Yes, they are.
I mean, excuse me for a second. I just want, okay, great.
1, 2.
Further one.
The one closer to the wall?
Yes.
Which one was that?
That's the sort of liquid.
The liquid one, okay. And in fact, if we had a slightly longer slope, the liquid one would come down first. Now, why?
Less than your masses.
We just pictured the frozen one being like a solid sphere, and the liquid one being more like the ring.
The liquid one, okay.
Except that there's no water up top.
Would be because the liquid, the mass would tend to stay towards the outside of the circumference?
Ooh. I don't think so, but that's,
I was going to say something similar there, just by capillary action, just by the fact that the liquid is mostly water, it's going to stick to the can, it's going to be closer to the perimeter of the cylinder.
interesting thought.
That's opposite.
Interesting.
I thought about the wheels you were talking about on the train yesterday.
The wheels on the train, right?
So maybe the liquid is shifting to adjust so that it just overcompensates or cancels out any, extra.
Okay, but the liquid one got down first, actually.
Right. That's what I'm saying. So
Wait.
that would make it a little bit lighter because it's shifting all.
A little bit lighter. I don't know if I'd use that terminology, but you had a question or an answer.
I think the frozen one, the mass of the lemonade side has to rotate with the cylinder.
Okay.
And the liquid one, the mass of the water doesn't have to start rotating. It just kind of slides down with it.
How about this? Newton's first law, an object in motion tends to remain in straight line motion at constant velocity unless an outside force acts upon it.
Okay.
What that means is that the water is going to be pushed to the outside of the cylinder. It's going to try to continue in a straight line, and that will bring it closer to the edge of the cylinder,
Which edge?
the outside edge of the cylinder.
You mean this edge or this edge?
I mean, the
cylinder,
circumference.
yeah.
The circumference.
Closer to the circumference.
Okay, interesting.
Get closer to the rim.
Actually,
The water stays down.
okay. The solid, well, now it's semi-solid because it seems like it didn't freeze too well here. The semi-solid one really had, we would treat it as a cylinder, a disc with a moment of inertia, okay? The one with liquid inside, the liquid, you have to be solid to have a moment of inertia like this, a rotational moment of inertia, and handled this way. In this case, the liquid essentially slides down inside the container and does not contribute to the moment of inertia of the can, of the solid can. So it is actually faster, and you're absolutely right. He had the best answer. Okay? He had the best answer. It slides down. So if you have two objects and let's say you disregard friction and you have two objects. One is a cylinder and one is a box. So one is rolling and one is sliding. The box will always win because it's not rotating about an axis. The water was not rotating about an axis. It was just sliding down. Whereas the solid juice was kind of semi-solid in there, was in fact trying to rotate. It had a larger moment of inertia, so it would have lost. So very good, very good. Now, I heard something in this discussion that kind of relates to the very next demonstration. And I hope this one, I hope I have a long enough incline that this one will work. Okay, I have 2 Sprites I took from the soda yesterday. Again, all right. So I need someone to roll these down and let us determine that in fact they have the same moment of inertia. Just can we have someone else, someone new to do this? Okay. There's no surprises are in here. Yes. You just give me a second, I put this away. Okay, so let's just confirm, in fact, that they have the same moment of inertia. Let's watch them closely. Okay.
The one closer to the wall got down there a lot faster.
Yes.
Did it really?
Yes.
Is this thing stable? No, it's
Probably not.
Probably not.
No, it leans.
It leans.
It leans.
All right, let's
So
try
that's
it.
probably why the wall.
I like to stop it from jumping like that. Let's just see if we can do this.
We should put them both in the middle.
All right.
Try to put them on. You go now.
Go. Oh, God, they hit my fingers at the same time.
Yeah. You gotta put them on the book. So.
Okay. Basically, I think for within the accuracy of how much these are filled and everything, they should have the same moment of inertia. All right. So we're going to take one can and shake it up really good. All right. So what is she doing? What's happening inside? She's what?
Releasing the gas.
She's releasing the gas. She's
Okay.
pushing the pressure inside.
Okay, so now you're releasing some of the gas. But we haven't really changed anything. We haven't removed any mass. Okay, so now I want to roll them down and see what happened. Let's see what happened. Okay. So, by the way, so you can envision now with the liquid inside, okay, according to our previous little experiment, that while the can rotated, the liquid slid. All right. While the can rotated, the liquid slid. Okay. So let's see what happens now. This is the one that you're shaking.
Right.
We'll put it closer to the audience here. I have to catch. Yeah, I know. I don't think it was long enough to tell the difference. Is this the one?
So you need more shaking. You want me to shake it more?
Well, I don't know. Let's just. The one shaking hit the bottom first. Is that what it was?
Yeah. Slightly. Okay. You shake it some more?
Which is.
Well, you have to shake it for a longer period of time.
Of course, since we've been rolling them around, that one probably has a lot of gas in it too.
Yeah.
It's hard to tell. It's hard to tell with that. Okay. You can open it. I think if we had a longer ramp, we might be able to differentiate the difference between the two. And in fact, the one that was shaken will probably hit the bottom last. And why would that be? The shaken one would hit the bottom last.
More pressure
More pressure.
increases the friction between the liquid and the can, and so it has to rotate with the can rather than sliding.
Pressure. Okay. I think you're on the right track. I think the concept on this one, I'll just go on because we couldn't seem to quite differentiate the two. I'm not sure it's really clearly understood why the one that was shaken would hit the bottom last. Is that what I said? Yeah. Well, if it did, it would have a greater moment of inertia, right? Because the thought is that there'd be some adherence of the liquid to the sides of the can as a result of the gas. And therefore, it would increase the moment of inertia of the can, you know? So you have the liquid actually rotating with the can as opposed to sliding. And if it's adding to the rotation of the can, then it would have a larger moment of inertia and it would go down more slowly. Yeah, okay. All right, that's a little on the far end of things. I never did it. I'm obviously not going to do it again because it doesn't seem to work. Okay. All right, let's talk about torque. I want to skip ahead a little bit here. We've been looking at rotation, and you know, when we talk about linear motion, where we have a mass, we move an object, we move a mass by applying a force. Right? According to Newton's second law of motion, acceleration is equal to force divided by mass. Right? Force and mass. In rotation, first of all, we use moments of inertia instead of mass. And in order to get a rotation beginning, we use not just a force, but something that we call a torque. Okay. And torque depends on three things. It depends on the force you're applying, the direction you're applying it, and how far you are from the point of rotation. Okay. So, we have 6 groups in here. Okay. Can I have someone help me pass these out, please? And you also pass out a weight to each person. And you may need a little help here. Can we have another one? Another person? Every group. And give them one of these clamps. Each person that has a. Okay. So let's see, we have linear motion. And rotational motion. In linear motion, the resistance to motion is a inertia, or typically we call it mass. And the resistance to rotational motion is rotational inertia. All right. This is in kilograms. This is in kilograms meters square, so it depends on the distribution of the mass. That which creates motion is a force. And here, what creates rotational motion is torque. The units of force for linear motion is newtons. And for torque, it is newtons meters. Okay, so what you have in front of you is a a torque feeler. You're going to feel the torque. So if you could place, may I borrow this for a second? Why don't you place your little clamp at 50 centimeters to start, okay, and clamp it down so it'll stay there at 50. Okay. Now most of you have, I think, 100-gram weights, and one of you has a 200-gram weight. Who has the 200-gram weight? You do, okay. All right, so everyone able to get their little clamps on? Okay, so put your weight on the clamp and have one person hold it at the zero end, the zero end. You don't have a weight? You don't have a weight? Does anyone have an extra weight? There's a weight down there. Okay. So hold it out, you know, you can get a feel. Now, the torque, where is the axis of rotation at this point?
Your hand.
Your hand, okay. And the torque is the force, and the force in this case, hold that out straight, the force in this case is the mass times acceleration due to gravity. All right, that's the force. All right, so yeah, this mass times acceleration, so it's 20, what is it, 100? 100 grams times 9.8 meters per second squared, or 0.1 kilograms. Okay, and you can get a feel for the torque. Okay, the torque is the lever arm, which is this perpendicular distance from here to the axis of rotation, times the force. That's the torque. Okay. Now, keeping the exact same meter stick, the exact same weight, move your clamp to 75 centimeters. You might have to take the weight off to do it, especially with the 200 one. You guys have the hardest one. Give yourself a break. Let's just wait till everyone gets it here. All right, give your other people in your group a chance to feel it. I hope you had a chance to feel it at 50. Can you tell the difference? Mm-hmm. Is it more difficult? It's almost, you have to hold it on this end here. Yeah. Is it more difficult? You know, it's like the difficulty we had when we changed the axis of rotation with that orange rod, right? It's a lot, it feels, what's the term you used? It feels heavier, but is there any different weight there? No, it's the same. The reason is the torque is different. Because what's different? The lever arm, right. That perpendicular distance between the force and the axis of rotation. Okay, all right, now if you're really brave, move it down to like 95. Can you do it at 95? Give him the 200 weight, 200 gram. How do you do it? Ooh, she's good. Now, can you feel even more torque? Okay. So again, the same mass, the same mass, but a different torque. Okay.
Oh, yeah.
All right, now, there are lever arms everywhere, right? Unless you have a, what is the automatic flush with the light, the motion sensor, right? So a lever arm is the perpendicular distance from the axis of rotation. This would be the axis of rotation, and this is the perpendicular distance from the axis of rotation, and then that would be the force. Okay. Now, you know, even when, if you place it back at the 50 centimeters and put your weight on there.
That's a cheater pipe.
Sorry, what is that?
Place your thing back at 50 centimeters. Okay. You stand up. and hold it like this. Okay, can you hold it? No, hold it perpendicular to your maybe it's too difficult to do. Keep your hands.
Oh, like that.
Yeah. Okay. So this, what she's doing represents this here, right? The force is 90 degrees to the lever arm. Can you see how she's doing that? Okay. I don't know if you can do this. It makes it more difficult, right? Yeah. Well, no, you have to keep that. Yeah. I don't know if it's possible to do it. Yeah, there you go. Put your hand out. Is that difficult? More difficult? Okay. The lever arm, the lever arm is always the perpendicular to the force. Okay. If it's not perpendicular to the force, we have to do a slightly different calculation. Okay. It makes it a little bit more complicated. Now, on the other hand, if we increase the lever arm, anyone ever try to change a tire? Right, with those little things that they give you when you buy the car, it's like this big, and you're trying to, all right. So I went out and I went to Pep Boys and I got one of these big cross things, right, and had no problem getting it off. Why? I created more torque because I used a longer lever arm. It was fantastic, it was so easy. In fact, you could break the bolt, I guess, if you're not careful.
Worst things can happen. That's called a cheater pipe. That's
Yeah,
what they
or you
call
can
it.
add a pipe onto a wrench and do the same thing.
You can break the wrench that way.
Yeah, okay. So it doesn't, you don't think you have you personally might have the strength to break a wrench, but you could if you provide enough of a torque by adding the length of a lever, adding to the length of the lever arm. Okay. Now, it's torque that causes rotation. Okay. Now here's an example of an equilibrium situation. Equilibrium is when something remains stationary, not in motion, or is in constant velocity, not accelerating. Both of those terms mean equilibrium. In this case, we have equilibrium where we have something remaining stationary. Where is the axis of rotation of this particular little diagram?
The triangle.
The triangle. Right. This is the axis of rotation, okay. Let's take a look at the torques on both sides. So the torque as a result of this person at this axis of rotation is the distance what did I do with all my so torque T tau Greek letter tau is equal to force times, let's say, lever arm L. So in this case, what is the lever arm for the guy on the right? 1.5 meters. And what is his force? His force is his weight, and it's given to you as 500 newtons. So what is that value? Could someone give it to me? Yeah. 750 Newton meters. That's the torque about this axis of rotation, okay? All right, so if they're in equilibrium, that means they're not moving. That means the other side has to be equal to that. So let's take a look at the torque on this side. So for the girl, what's the torque?
250 newtons times 3 meters.
Okay, so the force, all right, let's give other people a chance. The force is what? I know you know, but it's the others. 250 newtons times 3 meters. 3 times 250, 750 Newton meters. Okay, the same torque. Let me ask you this question. Do you remember we talked about positive and negative rotation? Just hold off. Okay. I know, yes. Which way is this torque rotating? Clockwise or counterclockwise? Right, clockwise, right? It's going this way. It's tending to rotate this down. So if it's clockwise, is it positive or negative? Negative, great, negative. And which way is this one rotating? counterclockwise. So it's positive, right? So that becomes, so they're equal and opposite. And you have a stationary situation, right? It's in equilibrium. Again, torque creates rotation. All right, I have a question for you. I don't have a broom here. Let me see if anyone's out here sweeping. Oh, hold it a second. Hi. I have a special request. I need to borrow like a broom or something.
I've got that in the other closet. I'll bring it down to you.
It's for demonstration.
Right now? Okay, I'll go grab it.
Thank you.
You just need a broom or a dustpan too?
No. Just a long-handled broom. You know what I mean?
Okay.
Okay, thank you.
I don't have a push broom or anything.
What do you have?
Like just a regular broom.
That's fine.
Okay.
Okay, not to worry.
There she goes.
I have a question. If we go back again
Yep.
to that, and the picture seems to be at equilibrium, how will you determine which one is going to be clockwise, which one is counterclockwise?
Are we okay here? Biology is invading us?
Yes.
Okay.
Just by,
If you go back and look at some of the original slides we've had where we talked about circular motion,
yeah, I do recall
okay,
that.
and I said if we went in a counterclockwise, we always said that was negative. If we go
No, yes, back.
if I go counterclockwise, it's
It's
positive.
positive.
Thank you.
If we go-
Clockwise is negative. So kind of keeping that in the back of my mind, I look at just half of this guy, all right? So here's the axis of rotation. Now, which way is he tending to move about that axis of rotation?
Okay, so so he will go down.
He's going to go down, so he's going like this, right? Watch my finger. He's going like this, right? Is that clockwise or counterclockwise?
Clockwise.
So that's why it's negative.
So you assume then the other one is going to
I know, I don't assume it. I test it out. I look at it and I say, which way is she going? Which way is my finger to go if she were to let go and rotate? Look. Excuse me. Did I get you? Did I? Let me try more. Okay. So here they are rotating about here. One's here, right? So forget this side for a second, all right? Here's the person, and he is tending to rotate this way, right? So you said he was going clockwise, and therefore he's negative. Okay. Now here she is over here. Oh, thank you. Okay, you can stay and watch. Okay. If she's over here, right, and she's going to create this kind of rotation, which kind of rotation is that?
Oh, so it's not her.
Yeah, it's her. It's her over here. She's forget the side for now. If she got on that.
Got it. Got it.
All right. Okay. Thank you. So here we have. Come on in. What's your name? Amy. Amy is kind enough to contribute to this little experiment. So is this wood?
No, metal.
All right. So here's a broom. Okay, and it says, I need someone to balance this broom for me. Okay, I'm not exactly sure. See if you can balance the broom at one point. No. Okay. Oh, not bad. So, by the way, that would be the center of mass, right, of the broom, right, if she's balancing it. She's not quite got it, but she's doing well.
I'm balance impaired.
Okay, very good. All right. So let's say, okay, so you would agree that would be the axis of rotation. You have a certain equilibrium here. We have a certain equilibrium, which means the torque on both sides are
Equal.
opposite and equal, right? You all agree to that? Okay. So let's say I had a saw, and I sawed it. I don't have a metal saw. I sawed it right there, okay? And then I weighed, I massed each side, this side and this side. Okay, do they weigh the same? Thank you so much. Do they weigh the same? Talk it over with your group.
They would have to weigh the same because you have to balance each other out.
You had to balance it. You were at the center of mass, right? I'll draw a little picture. Oh, here it is. Okay, so this is. So this was the you agree this is the center of mass, even though we didn't talk about center of mass. That's the center of mass. We'll talk about it when we meet on during the year. All right. So you agree if that's the center of mass that this mass here, right? This mass should equal this mass. Is that what you're saying? If I sawed it right there?
No, because it's small. You have to think about the seesaw, the kids on the seesaw. Even if you cut the seesaw in half, that one kid still weighed a lot more than the other.
How can that be? How can that be?
Is the length, is the distance.
Did I have equal torques here? Okay, so we agree that's an equal torque because we had an equilibrium. Okay. And what is a torque? Force times. What are the forces here? What are the forces on each side of this point of equilibrium? The mass, the masses, right? But what?
No.
Oh, okay, okay. So, what weighs more, the broom handle or the brushes, or do they weigh the same, and why? You say the brush handle weighs more or less? Yes.
The brush would weigh more because the length is less.
Okay, the brush weigh more. All right. And in fact, if you had a broom this big, that was a little broom. Actually, I have one of these in my garage. I could have brought it in, but I'm not going to bring that in. I'm bringing so much junk. Yeah, they don't weigh the same, even though it looks like you're balancing over the center of mass, doesn't it? Because in this particular case, we're balancing torques, which is mass times length. So if this was longer here and this is shorter, that means this mass would have to be greater, right? So the masses are not the same, even though when you first think about it, if I'm balancing it over the center of gravity, you would think the masses would be the same. But now, in more advanced physics with torque, it's the torques that are same. The torque, so that if the torque can equal the torque on both sides, but that doesn't necessarily mean the masses are going to be equal to the mass because we have different lengths on both sides. Okay? Great. Yes? Thank you for holding back.
Yeah, you're welcome. You're welcome. Inference.
Yes?
If you have an object and you want to determine the average center of mass and be correct, you have to have an object with uniform distribution of mass.
That's right. You're assuming a uniform density distribution of the mass. Thank you. Okay, but I just was trying to look at this side. Great. Okay, I see we have 20 minutes, and what I wanted to do is I have one more exercise, but it requires that we go upstairs into the education library, all right? And I need 6 volunteers, and it's going to be an introduction to what we talked a little bit about already, which is centripetal acceleration, okay? Because I want to talk about centripetal force. I'm going to skip that for now. Oh, what's this? Oh, here we go. Here's the, this is, I forgot why I wanted this, right? We had the ladybug in motion, in rotational motion. You looked at the velocity and acceleration of the ladybug, okay? I didn't take it any further at that point, but we are going to take it further. That is, what causes this centripetal acceleration? All right, what causes it? It's a force. Force causes, all forces cause acceleration, right? Over here, we have, let me just complete this side. We had, from Newton's second law, force is equal to mass times acceleration. And on the rotational end, we have torque is equal to moment of inertia times alpha, which was angular acceleration. Remember, we were looking at angular acceleration or rotational acceleration, right? Okay. Upstairs, follow me upstairs. You can leave all your stuff here. You want to bring it with you? Bring it with you. Yeah, in fact, let's do this. Why don't you pack up, because you're going up to 212 right afterwards, okay? I need 6 volunteers, and the rest of us will observe what's happening. And it has to do with trying to move a ping pong ball in rotational motion and how to do it, okay? Yeah, you volunteer for anything?
Don't be shy.
All right.
Wait a second.
All right, so put all your stuff down if you volunteer. And evenly distribute yourself around the table. Now, the object here is you want to get the ping pong ball and move it in rotation around the table in a circular fashion. Okay? So you're going to use the straw and your mouth.
Nah.
Yeah, so you're going to want to get down here probably, right? And move the ball in rotation. First of all, are you going to go counterclockwise?
Let's see.
Does it matter?
Well, you want a circle. Whoops.
It's crazy.
You'll just take a little practice.
Yeah, right. People will be hyperventilating.
What the heck?
Let me take your picture.
Oh,
How do you take it? You taking a movie or you taking?
it's a movie, just push the top one.
All right.
Oh, good. You can see a little bit.
You just bat it in a circle.
No, you want to.
Oh.
Have a good gap here. Want to get another person in here with a straw, or
Move around.
move around, or one or the
Yeah,
other?
we have enough people.
Yeah, we need one more person.
One more person with a straw.
Come on.
Jay.
He-Man, come on, He-Man.
Right up.
Guy in the orange shirt.
Liars.
I could hide the corner with this on. Well, we'll both jump in there.
Oh, let's see your talent.
More straws you would have to.
Yeah, really.
So the idea is circular motion. Nice, smooth circular motion.
Well, here we go.
Circular motion.
I got skipped.
Whoa. Whoops. Whoops.
That's not circular.
Linear motion, right?
Zigzag.
Circular motion. Whoops.
It's hard. Yeah, it is.
This would keep your kids quiet for a while.
That's a great idea. Everyone get a straw.
You had it there going for a while, but now you seem to have lost the circular motion ability.
We got it one time.
You
Come on,
did,
just
you
a little
did.
credit.
You don't have to go on the edge. You could
But
make a
it's-
smaller circle in the middle of the table.
Okay.
That might.
See, we're shooting across instead of an angle.
It's the table.
Oh. What happened?
Yo.
So what's the secret here?
Yeah, really.
Do we all need to blow into the center?
Maybe so.
Gosh,
She's competing.
Yeah.
All right, we got it in the center.
Is it going around in a circle?
It was.
What was the trick?
All blow
We were all blowing
Don't
at
have it
the
on the
same
edge.
time.
You're all blowing at the same time, you're all blowing which way?
Toward the sun.
Mm-hmm.
So the force was,
There it is, all right.
the force was center located, centripetal. Will you remember this when I see you in September? We can talk about it?
Yeah.
Keep your straws, I don't want them back. All right?